Well, we're here at the 2020 Energy Technology Science Conference up here in Coeur d'Alene, and just to give you a quick update about what we're doing here. We were invited to this conference here last year. We were able to basically let people know that we had that we're working on Tesla technology concerning his turbine. Since that conference, we have expanded tremendously with our research and development due to some very generous donations from the attendees here, and we have now created a metal turbine. In fact, we were able to take the plastic turbines that we have been creating and then now make them into metal. We are so close to having this technology developed that maybe in the next month we'll even have our final prototype completed, so that anybody would be able to have one of these. One 4-inch metal Tesla turbine would power approximately 4 homes. That's how much power it makes. We do make a metal aluminum turbine, which is only a 3-inch model, and that will power 1 home. And so our goal here is to create enough energy for anybody to be off-grid, to be self-sufficient, and have all the power they need to power their home. Heat, air conditioning, cooking, whatever. There'll be plenty of it. I personally want to have a metal turbine so we can do some welding, and that's certainly possible. So we're getting real close at this point to having that finally completed. This conference has been just an incredible experience of like-minded people. The support that we have experienced here is overwhelming. It weighs 17 pounds at this point. Now, what's beautiful about that particular unit is that it's scalable. So if we wanted to make a 6-inch, 9-inch, 12-inch, 21-inch turbine, we could do that. Of course, at those scales, we're talking about powering cities. Our 3-inch aluminum turbine will actually power a house, but our 4-inch turbine will power about 4 houses. So, and then of course the bigger the scale, the bigger the power output, and the more energy power that you can produce. This is total open source. The whole project is open source. Our plans are CAD drawings for actually producing turbines are going to be available to anyone for like $50, right? And that means that anybody who wants to build one themselves is more than welcome to do so, or if they want to take it down to the local machine shop and create a business out of it and create turbines for people. Yeah, absolutely. We want everybody in the world to make turbines. The reason is that the turbine can be used to not only make every household independent, but it can also revolutionize industry. You can use it on trains, planes, automobiles, boats, spacecraft. It doesn't matter. You can hook it up to anything you want. You can desalinate seawater. You can actually pull water right out of the air in the desert and make water. The sun shines most of the day, and that energy can be stored and used at the nighttime as well as in the daytime. When like for instance, if we were to hook up a turbine to a vacuum system, so that you have a heat source and then you have a cold source. The heat will run towards the cold. It's like positive electrons run towards negative electrons. High pressure runs towards low pressure. It's like a tornado in a box. When you look at a tornado or a hurricane, what happens is the heat meets the cold, the high pressure meets the low pressure, and what do you have in between? Lightning. That is the energy transfer of those molecules into a lightning bolt. In the turbine, the same thing happens. We take the heat out of those molecules and we turn it into motive force. It turns a shaft. The shaft will turn a generator, and then the generator will do whatever you want it to do. So there's all kinds of different applications here. Well, Tesla called that a terrestrial power plant. For instance, let's just say that you're in the Arctic, all right? And you've got this really cold, surface temperature. The Earth is 55 degrees. There's your warm source. You have to have a differentiation of heat of 55 degrees to run a turbine. But once the turbine is going, you only need a 1 degree differentiation to keep it running. So that's pretty simple. No, you've got a your Earth is 55 degrees. It's freezing outside. There's definitely a 30 or a 55 degree differentiation there, and the turbine will take that heat, turn it into motive force. You run whatever electrical power needs you have, and that will just keep going. Now, in a desert, you have really hot air on the outside. You could use a river for your cold source, right? Well, maybe not in the desert so much, but you could actually use the Earth as 55 degrees. If it's 100 degrees outside, if it's 110 degrees outside and you got 55 in the Earth, guess what? You've got that differentiation. You can start your turbine. The other thing you can do in a desert is you can actually increase the temperature by creating a water bank, a thermal solar water heater, and you can actually boil water. Our first 4-inch turbine was only on our testing bench here just about a month ago. We found that in running that particular turbine, we saw some problems that need to be fixed. It went back to the machine shop. Those problems were fixed, and once they were fixed, we found other problems that were realized. We fixed those, and the next turbine is going to be on our bench in the next week or two, and then we will see where the efficiency of that engine is going to work. So in the last turbine that we just got through modifying, it ran for 4 days at 20,000 RPM straight, and then we kicked it up to 47,000 RPM to see if there's any problems, and there was no problems. So we have a lot of high hopes that we won't have too many corrections that we're going to have to make on that one, and if it comes back true, then of course we're going to go into production. It's all about Tesla. There's nothing new under the sun, they say. We have no claims whatsoever that we're so smart that we did this. No. Actually, Tesla ran a 9-inch turbine. Yeah, he ran a 9-inch turbine, and he predicted in the early days that his turbine would get 10 horsepower per 1 pound of turbine. Later he said it was 20 horsepower per 1 pound. If it's somewhere in between, I'm good, Well, what the heck? You take let's just say you've got a 20-pound turbine, and if it's 10 horsepower per pound, well, there's a 200 horsepower engine, and that's only 20 pounds. Whoa. Or it's only 10 pounds actually. It's only 10 pounds. So that's incredible. Compared with a 500-pound engine that gets 200 horsepower, that's wow. That's incredible. It would change aviation. I mean, obviously, the lighter your craft when you're trying to fly, the better off you are. The faster you can go, and the safer it would be. We're at iEnergySupply.com. We also have a YouTube channel that is iEnergy Supply. We have presently about 41, 42 videos that actually shows the progress that we have attained in the last year and a half, and it shows the very beginnings of where we started. You have to realize that when we started this, we knew nothing about turbines. In fact, my partner and I, we just created what was called a geometrically aligned lateral toroid generator, and called the GALT. And what happened is, physics teaches us that when you have a generator and you put a load on it, the generator slows down. And if you short out the generator, it absolutely stops. Now, when we built our generator, when we put a load on it, it went faster. And when we shorted it out, it went even faster. So we all of a sudden realized that Lenz's law is not a law. It's more of a suggestion, but it works in closed systems. In a closed system, then it will just decrease the energy. But in an open system, it actually increases it. At that point in time, I looked at my partner, Jeremiah, and I said, look, what was Tesla's most prized invention? Because he had like over 300 patents or something like that. And without a blink of an eye, he said, his turbine. I go, let's build one. So we started building one. We got help from people around the world as we started to investigate the various Tesla patents. And we found that Tesla never patented his design in any one place. So we got patents from England, we got it from the US. We found 33 patents from Bulgaria, Serbia, I mean, and that were never patented. Gems, golden gems of information that Tesla never had patented because they didn't patent them, because they worked. And it was threatening the oil industry. It was, no, we can't patent that, so they didn't. But we found gems of information that. And then in the process of studying that information, we came to the realization that Tesla never took the turbine and connected it to the pump. He said that if you take the turbine, any turbine, not just his, any turbine, and you connected the Tesla pump to it, it would increase the efficiency of that turbine 50 to 100%. So obviously we hooked up a pump to it, and that's what we are basically showcasing here at the Energy Conference. We have a Tesla pump hooked up to the turbine, and yeah, it works. It works well. Now we just have to get a few bugs out of it, and the biggest bug that we're dealing with right now is the balancing issue. When you're running at high RPMs, it better be balanced, or you're going to have a disaster on your hands. And we've seen a few disasters. All you got to do is go to iEnergy Supply at YouTube and see some of the turbines we've blown up. It's pretty exciting. So when the 4-inch turbine is actually made out of stainless steel, and our particular turbine has a titanium, not titanium, but an Inconel case. Inconel is the hardest material that I know of, and this is a material that has a nickel alloy composite, and what it does is they use this on the space shuttle, on the nose of the space shuttle. So when it's coming through the atmosphere, all that friction of coming through that atmosphere creates a lot of heat. And Inconel, when it gets over 100 degrees, creates its own heat shield. It's like really strong. And we want to run a plasma pulse jet through it. And that means high heat. And we've run the pulse jet through our plastic turbines. And of course, we melted them, warped them, and blew them up and all that good stuff. But with a metal turbine, you can run high heat through them, and you're not going to get that warpage or that you would get with plastic. So it's a much more durable design. And so you can run steam through it, for instance, high heat steam for that matter, and it will run quite efficiently. Again, if you can just boil water, run it through your turbine, you're going to have all the power you need. Oh, absolutely. We would love to make it out of graphene. I mean, that's our ultimate goal. Ultimate. We want a graphene discs to run in that turbine because we think that we can get some extremely high RPMs out of it, even supersonic. Oh, the faster you go, the more energy you produce. So if we can go the speed of sound, Mach 1, Mach 2, Mach 3. Now, when you put this in a vacuum, your RPMs are unlimited. It's just not unheard of to go, 500,000 RPM. You're in a vacuum. There is no friction, especially running air bearings. There's no friction. So you can go as fast as you want, as long as you have good balance. But with air bearings, the shaft is suspended in air. And if there's any wobble whatsoever, it would all be compensated by the air around it. So it automatically would correct itself. Even if it wasn't balanced, it would correct itself. So, and then of course the beauty of air bearings, of course, it's never going to wear out. Well, if you're running on a vacuum, it will implode instead of explode. It's totally safe. You can stand right next to it. It's going to implode. If you were, let's say you're running on compressed air, for instance, and it's going really fast, and you get beyond critical, and it explodes. The Lexan casing itself is bulletproof. We've blown them up, and it's bulletproof. So it's very little damage would happen. We actually had a turbine that disintegrated pretty much inside of its Lexan casing, but it was all contained within the case. Now we actually had a turbine that we ran in, and I know this sounds weird, but this was actually prototyped out of wood. It had a wood casing on it with just plastic rotors on it, just to take a look at the some of the dynamics that was going on, and it exploded. Unfortunately, the rotors hit the side wall and it just blew up. But there was a Lexan, half-inch Lexan sheet above this particular experiment that we were doing, and when it exploded, I mean, there was pieces in the wall over there was pieces in the wall over here, but there was no damage to any people at a particular time because the Lexan protected. Again, it's bulletproof, so very, very little risk of injury to anybody. And of course, if you're running under vacuum, it's just gonna implode. So no damage. Just got to get a new turbine. No, I don't think anybody's going to run it that fast. Seriously. Yeah. Now, the other thing that you can see at the iEnergy Supply YouTube channel is we actually took a Newman motor, modified it slightly, and made it into a Newman generator. What we did is we took a diametrically opposed magnet, put it on the shaft, and we spun that thing. And then we took a diametrically opposed magnet and put it on the Newman generator. As fast as this magnet spun, this magnet magnetically locked to it, and it spun just as fast. And then we took another Newman generator with another diametrically opposed magnet and put it next to that one, and that one spun. And then we put another one on, and that one spun. You can have, I don't know, how much power do you need? No wires. This is, well, we just call that. That is the wireless transmission of motive force. Now, we all experience wireless transmission just by pulling out your phone, and you've got wireless transmission, right? But where do you see wireless transmission of motive force? Which makes you wonder, why are there belts on cars? You don't have to have a belt, just magnetically couple it. That's how you do it. Well, you have to understand those cars were made 100 years ago. That's 100-year-old technology. And of course, they didn't have neodymium magnets back then. So we're going to be testing the forces, the centrifugal forces of various metals to find out where their breaking point is. Let's just say that, for the sake of argument, it's 200,000 RPM and aluminum, falls apart. So you never run it over 100,000. This is that simple. But we have to find out what those values are. We don't know yet. But we will find out, and of course we'll just let everybody, don't run it over 200,000 RPM. You have risk of it,